All right, in this video, I'm going to help give you some ideas of things to choose for your project. What sort of unsolved problems, what sort of topics will you work on? So the first step is to pick an unsolved problem in a topic to investigate. So you should think about, you should pick something that sounds interesting to you, plays to your strengths, or involves another area of mathematics that you're interested in. For example, I've put the Hamiltonicity of Cayley colored digraphs as a potential topic for this project, and that involves some group theory. So if you're really into algebra and you like group theory, you could do some work on that. If you're interested in coding and programming, I have a topic for that occurs in, I believe that I have it in the highly connected graphs section of the topics list. Don't be afraid to choose a topic you don't know much about. Like I said, I'm going to give you a brief introduction here because we haven't encountered a lot of these topics in the class yet. But the great thing about this class is we now have a nice base of information, a sort of base level of understanding of graph theory that now you can go off and learn very specific topics in graph theory. And so don't be afraid. If you've never heard of a topic before or haven't done anything in it, that's totally fine. You should now be able to go and learn some of that. And I'm here to help you along the way. But I assure you, you have a good enough understanding of graph theory to now learn some of these more specific topics. Also, don't be afraid to go off script, right? So I'm going to give you a list of topics. You do not have to pick one of these. I'm also providing you with some resources for finding other unsolved problems, like the Open Problem Garden. So you don't have to pick one of the topics I'm going to mention. Don't feel restricted to that. There's lots of unsolved problems in graph theory, and so I do want you to explore and find something that you like. All right, so let's get into the first topic. So the first topic I'll mention is graph labellings. So graph labeling is an assignment of labels to either the vertices or the edges of a graph, and in some cases both. And actually, in a lot of cases, some of the most highly studied problems in this is where a vertex labeling is given, and then there is some rule for inducing an edge labeling based off of that vertex labeling. In particular, there's the topic of graceful labellings. So these are covered in our textbook, so this would be a good place to start if you're interested in this. And this is in Chapter 13, Section 4 of our text. But I'll give the definition here. So let G be a graph of order n with m edges. A vertex labeling of G is graceful if, so a labeling, we can think of a labeling as a function from the vertices to a set of labels. So here our set of labels are the integers 0 through the number of edges in the graph. So we label the vertices with those numbers. And this function from the vertices to labeling, this labeling is 1-to-1. So this means that every vertex is given a distinct label. And the induced edge labeling, so we induce an edge labeling on this. So from the edges to the set of integers 1 through m by the label on an edge, uv, is the positive difference of the two labels on the incident vertices. So the idea is we want the vertex labels to all the vertices get distinct labels in such a way that when we induce this edge labeling, when we take the differences of the vertex labels at each edge, that's also a 1-to-1 labeling. That is also all the edges get distinct labels. All right, so this maybe seems a little bit confusing, so let me give you an example. It's really not too difficult, but we use all this highbrow language to describe them. And then one term here is that a graph that admits a graceful labeling, so a graph in which we can actually do this, produce such a vertex labeling that induces this edge labeling, is called a graceful labeling, and we call that graph graceful. So here's an example of a graceful labeling of K4 minus an edge. So here we have 4 vertices, K4, and we've removed one edge from K4. And so this graceful labeling, or this labeling is given, so right, this vertex labeled 1, 0, 3, and 5. So that vertex labeling is given first, and then we induce an edge labeling by taking the positive difference of incident vertices. Right? So this edge is labeled 1 because its incident vertices are 1 and 0. This edge is 4 because its incident vertices are 1 and 5, and so on and so forth for each edge of the graph. And so now we have an edge labeling of the graph, and notice that every edge here is given a distinct label. Right? 1, 3, 2, 4, 5. No edge label is used twice, and no vertex label is used twice. And so this is what's called a graceful labeling when you can do this. That's a graceful labeling. Hence, the complete graph on 4 vertices minus 1 edge is a graceful graph. So what's the big conjecture with graceful labelings? Well, these have been studied since the 60s or 70s. But there remains a major unsolved problem in the topic, and that is the graceful tree conjecture. So the graceful tree conjecture is that every tree is graceful. So given any tree, we can find a graceful labeling of it. That is still an unsolved problem, and it's a nice one for this topic because you can look, there's lots of different trees out there. You can look at a lot of different trees, find graceful labelings on them, and there's so much great history on this problem, on this conjecture. You'll be able to make a really nice paper and presentation on it, I think. So there's also a quick variation of this problem that leads to another unsolved problem. If you want to, I don't know, maybe get a little bit more interesting, move away from graceful, or if maybe someone else has already wanted to do their project on the graceful tree conjecture, maybe you want a similar one. So this is called harmonious labellings. So remember, in the definition of graceful labellings, we induced an edge labeling by taking the positive difference of the incident vertex labels. So what if we took the sum of the incident vertex labels? Well, this would be really easy if we allowed it'd be really easy to find distinct one-to-one edge labeling if we had no sort of restriction on this. So what we do is we take the sum in the integers modulo m, the number of edges, and that way there's only m labels possible for the edges, and so this gives us the same sort of restriction that we have for the for graceful labelings, but now we're taking sums inside of integers modulo m. And a graph that admits a harmonious labeling is called harmonious. And so, of course, we have the harmonious tree conjecture. Every tree is harmonious. So again, this is a nice topic to work on because you can look at a lot of different trees and give harmonious labelings, determine classes of trees that are harmonious, and look at the history of this topic. So this is a fun one. In the next video, I'll talk about some variations of highly connected graphs. I'll see you there.